Hey everyone, and welcome back to the channel. I'm absolutely thrilled you're here today because we're about to embark on one of the most mind-bending journeys through the most mysterious and distant frontier of our solar system. Now, I know you might be thinking, space is cool and all, but what's left to explore? Well, my friend, buckle up, because we're going beyond Neptune, beyond Pluto, into a region so vast and enigmatic that we're still scratching our heads about what we found out there. This is the story of the Kuiper Belt's hidden worlds, those icy, ancient fragments of our cosmic past that have been silently orbiting our sun for billions of years, preserving secrets that could rewrite everything we thought we knew about how planets are born. Before we dive into this frosty cosmic wilderness, do me a huge favor. Hit that like button if you're ready to have your mind blown. Subscribe if you want to join our growing family of space enthusiasts. And drop a comment telling me where you're watching from and what time it is right now. I love seeing people from all around the world tuning in, whether it's morning coffee time in London or afternoon tea in Tokyo. Your comments really help build this incredible community of curious minds, and I read every single one of them. Now, let's start our journey. Picture this. You've just left Neptune behind, that beautiful blue ice giant that marks what most people think of as the edge of our solar system. But space doesn't just stop there. Oh no, that would be far too simple. Instead, you enter a region that stretches from about 30 astronomical units all the way out to 55 astronomical units from the Sun. Now, to put that into perspective, 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles or 150 million kilometers. So, we're talking about a region that starts 2.8 billion miles from our star and extends out to over 5 billion miles. That's a lot of space, and it's filled with something absolutely fascinating. Astronomers call this vast, donut-shaped region the Kuiper Belt, named after the Dutch astronomer Gerard Kuiper, who, back in 1951, proposed that a disc-shaped region of icy objects beyond Neptune might exist from which comets originate. Interestingly, Kuiper himself actually believed this region no longer existed, that it had been emptied out long ago, which is a bit of cosmic irony since we now know it's one of the most populated and intriguing zones in our entire solar system. Now when we say belt, don't picture something thin like a rubber band. The Kuiper Belt is enormous, one of the largest structures in our solar system, a massive flattened disk tilted only slightly from the plane of the planets. Within this incredible expanse, scientists believe there are millions, yes, millions of icy bodies, remnants from the formation of our solar system about 4.6 billion years ago. These aren't just tiny specks of dust, either. We're talking about objects ranging in size from small comets just a few kilometers across to dwarf planets hundreds, or even over 1,000 kilometers in diameter. In fact, astronomers estimate that there could be hundreds of thousands of objects larger than 100 kilometers across, and perhaps 1 trillion or more comets scattered throughout this region. The total mass of all this material is estimated to be somewhere between 1 and 10% of Earth's mass, which might not sound like much. But when you consider how spread out everything is out there, it's actually an astonishing amount of ancient material. So what exactly are these things made of? Well, unlike the asteroid belt between Mars and Jupiter, which is primarily rocky and metallic, the Kuiper Belt objects are icy, really icy. They're composed primarily of volatile compounds that would have evaporated or sublimated closer to the Sun. We're talking about water ice, frozen methane, frozen ammonia, and other exotic ices. These materials are the frozen building blocks of the outer solar system, preserved in a deep freeze so far from the Sun's warmth that they've remained essentially unchanged for billions of years. Think of them as time capsules, cosmic fossils that have been locked away in a cryogenic vault since the very beginning of our solar system story. When sunlight hits these icy surfaces, some of the materials vaporize, creating thin atmospheres that freeze again when the objects travel farther from the Sun in their orbits. It's a constant cycle of freezing and thawing on a cosmic timescale. The story of how we discovered this frozen frontier is almost as fascinating as the region itself. The first Kuiper Belt object to be discovered was actually Pluto, way back in February 1930 by Clyde Tombaugh at the Lowell Observatory. At the time, of course, nobody knew Pluto was part of a much larger population of similar objects. It was just this mysterious, tiny planet that orbited way out at the edge of the known solar system. For decades, Pluto remained an anomaly, an odd little world that didn't quite fit with the other planets. Some astronomers, like Gerard Kuiper, speculated that there might be more objects out there, but proving it was another matter entirely. The problem was that these objects are incredibly faint and unimaginably distant. Imagine trying to spot a mountain-sized chunk of ice and rock that's billions of miles away, reflecting only the tiniest fraction of sunlight back toward Earth. It's like trying to see a single snowflake in a blizzard from miles away. The technology simply didn't exist to detect these objects routinely until the late 20th century. Then, in 1992, everything changed. Astronomers Dave Jewett and Jane Liu, working at the University of Hawaii, made a breakthrough discovery. After 5 years of painstaking searching using the powerful telescopes at Mauna Kea, they found a small body orbiting the Sun beyond Neptune. This object, eventually designated 1992 QB1, was the first classical trans-Neptunian object to be discovered, and it opened the floodgates. Since then, astronomers have discovered over 2,000 Kuiper Belt objects, and every year we find more. The reason it took so long is simple. These objects are so small and so far away that they appear as nothing more than faint points of light, even in our most powerful telescopes. Most of them look like tiny dots, barely distinguishable from background stars, which is why spacecraft visits are so incredibly valuable. They're the only way to see these worlds up close. Now, let's talk about how this incredible region formed, because understanding its origins is key to understanding the entire story of our solar system. The leading theory among astronomers is that the Kuiper Belt objects are leftover building blocks from the formation of the solar system, the planetesimals that never got incorporated into planets. In the early days of our solar system, about 4.6 billion years ago, the region beyond Neptune was much more densely populated. There may have been as much as 7 to 10 times the mass of Earth in material swirling around out there in a massive disk of icy bodies. These were the raw ingredients for what could have been another planet, maybe even several planets, if things had played out differently. But they didn't form into a large planet, and we have Neptune to thank or blame for that. As the giant planets were forming closer to the Sun, they were migrating, moving through the protoplanetary disk, interacting with all the smaller bodies around them. Neptune, being the outermost of the giant planets, had the most significant interaction with this dense disk of icy material. Its powerful gravity stirred up the region so much that the small bodies couldn't coalesce into a larger planet. Instead, they remained as individual objects, forever destined to be the also-rans of planet formation. Neptune's gravitational influence didn't just prevent them from forming a planet, though, it also scattered most of them away. As Neptune migrated outward through the disk, it flung countless icy bodies inward toward the other giant planets. Jupiter, with its enormous mass, acted like a cosmic slingshot, hurling most of these objects out of the solar system entirely, or into extremely distant orbits that would eventually form the Oort cloud. By the time the migration was complete, only a small fraction of the original material remained in what we now call the Kuiper Belt, a ghostly remnant of what was once a much more massive population of icy bodies. This process of giant planet migration is supported by what's called the Nice model, named after the city in France where it was developed. The Nice model suggests that the early solar system was much more compact than it is today. The giant planets likely formed in a chain of orbital resonances, much closer together, and there may have even been a fifth ice giant that was later ejected from the system. Surrounding these planets was a massive disk of leftover planetesimals, maybe 20 to 30 Earth masses in total, extending out to about 30 astronomical units. Over millions of years, gravitational interactions between the planets and this disk caused the planets to migrate. Saturn, Uranus, and Neptune moved outward, while Jupiter moved slightly inward. At some point, about 500 to 700 million years after the solar system formed, Jupiter and Saturn crossed a 2:1 orbital resonance. That is, Jupiter's orbital period became exactly twice that of Saturn's. This gravitational dance triggered a dynamic instability that shook the entire outer solar system. The extra ice giant was ejected, the remaining planets settled into their current orbits, and the planetesimal disk was almost completely dispersed, with a small fraction being captured as Kuiper Belt objects, some becoming the Trojan asteroids that share Jupiter's orbit, and others being flung into the Oort cloud. This might sound like just a theoretical story, but there's compelling evidence for it. The most dramatic example is Pluto itself. Pluto is locked in what's called a 2:3 orbital resonance with Neptune, meaning it completes exactly 2 orbits around the Sun for every 3 orbits Neptune makes. This isn't a coincidence. It's a fossilized record of Neptune's outward migration. As Neptune slowly moved outward through the ancient planetesimal disk, its gravity captured objects into these resonant orbits, shepherding them along like a cosmic sheepdog. Pluto and many other objects, called Plutinos, are stuck in this gravitational dance, preserved as evidence of Neptune's ancient journey. The distribution of these resonant objects, along with the overall structure of the Kuiper Belt, matches what computer simulations predict from the NICE model, giving astronomers confidence that this really is how our solar system's outer frontier came to be. Now, the Kuiper Belt isn't just a uniform scattering of icy rocks. It's actually organized into several distinct populations, each with its own story to tell. Understanding these different classes of objects is like reading different chapters in the history book of our solar system. Let's start with the cold classical Kuiper Belt objects. The term cold here doesn't refer to temperature, although they are incredibly cold, but rather to their orbits. These objects have nearly circular, uninclined orbits, meaning they travel in fairly perfect circles close to the plane of the solar system. They're located in a relatively narrow band between about 42 and 48 astronomical units from the Sun. Cold classical objects are generally small, with none larger than about 500 miles across, and they tend to be redder in color than other KBOs. Astronomers believe these objects are the most pristine, the most untouched by the gravitational chaos that affected the rest of the solar system. They likely formed right where they are today, in a dynamically calm environment, and have remained there for billions of years, preserving the original material and conditions of the outer solar nebula. They're the purest time capsules we have, the least altered since their formation. Then there are the hot classical Kuiper Belt objects. Again, hot refers to their orbits, not their temperature. These objects have more elliptical, inclined orbits. While they're found at similar distances as the cold classicals, their orbits can carry them much farther from the Sun during parts of their journey. Hot classical objects tend to be larger than their cold counterparts and are generally grayer in color. They likely formed closer to the Sun and were scattered outward by gravitational interactions with the giant planets, particularly Neptune, before settling into their current orbits. They're the immigrants of the Kuiper Belt, born elsewhere but relocated to the outer frontier. Another important group is the resonant Kuiper Belt objects. These are objects that have been captured into orbital resonances with Neptune, just like Pluto. The most common resonance is the 2:3 resonance, where objects make 2 orbits for every 3 of Neptune's, but there are others too. Some objects are in 1:2 resonance, 1 orbit for every 2 of Neptune's, 2:5 resonance, and various other ratios. These resonant objects are like cosmic hitchhikers, locked into gravitational relationships with Neptune that keep them in stable orbits. They were captured during Neptune's outward migration and serve as some of the best evidence for the NICE model. The fact that we see distinct populations in these resonant orbits with specific characteristics tells us that Neptune's migration was slow and steady, not a rapid jump. The scattered disk objects represent another fascinating population. These objects have highly elliptical, unstable orbits that can take them on wild journeys from relatively close to Neptune's orbit all the way out to hundreds of astronomical units from the Sun. Their orbits are chaotic, and they're constantly being perturbed by Neptune's gravity. Many astronomers believe these objects started as part of the more stable Kuiper Belt populations, but were scattered into their current orbits by close encounters with Neptune. They represent the ongoing dynamical evolution of the outer solar system, objects that are still being shaped and moved around by gravitational forces. Some of these scattered objects can even become short-period comets if they're perturbed inward enough to approach the Sun and develop Haumea tails. Speaking of comets, this is one of the Kuiper Belt's most important roles. The Kuiper Belt is the primary source of short-period comets, those comets that complete their orbits around the Sun in less than 200 years. Famous comets like Halley's Comet are believed to have originated in the Kuiper Belt before gravitational interactions, with the giant planets sent them on trajectories that bring them closer to the Sun. These dirty snowballs provide a rare opportunity to study the primordial material of the solar system up close. When they approach the Sun and their ices vaporize, creating those beautiful tails, they're literally releasing gases that have been trapped since the birth of the solar system. By studying these comets, scientists can learn about the chemical composition of the early solar nebula, the conditions that existed billions of years ago, and perhaps even clues about the origins of water and organic materials on Earth. Now let's talk about the celebrities of the Kuiper Belt, the dwarf planets. These are the largest members of this icy realm, worldlets that are massive enough to be round due to their own gravity, but not quite massive enough to clear their orbits of other debris, which is why they're classified as dwarf planets rather than full planets. The most famous, of course, is Pluto. When New Horizons flew past Pluto in July 2015, it revolutionized our understanding of this distant world. We learned that Pluto is anything but a dead, static ice ball. It's an active, geologically dynamic world with a complex surface that tells a story of ongoing change. Pluto has 5 known moons: Charon, which is so large compared to Pluto that they actually form what's called a binary system, orbiting a common center of mass, and 4 smaller moons: Styx, Nix, Kerberos, and Hydra. The images from New Horizons revealed breathtaking features on Pluto. There's Sputnik Planitia, a vast, heart-shaped plain of nitrogen ice that's completely free of impact craters, indicating it's geologically young, perhaps less than 10 million years old. The ice in this region flows like glaciers, slowly moving across the surface, and there are evidence of ice mountains made of water ice that rise up to several kilometers high. Perhaps most astonishingly, there's evidence that Pluto might have a subsurface ocean of liquid water beneath its icy crust. This is revolutionary because it means that even at these incredible distances from the Sun, where temperatures hover around -375 degrees Fahrenheit, internal heat sources can keep water liquid. This heat likely comes from radioactive decay in Pluto's rocky core and maybe some residual heat from its formation. The thought that there could be an ocean beneath Pluto's surface, protected from the frigid cold by miles of ice, is one of the most exciting discoveries in planetary science in recent decades. Then there's Eris, discovered in 2003 from data collected in 2005. Eris is roughly the same size as Pluto, with a diameter of about 2,326 kilometers, making it the most massive known dwarf planet, about 27% more massive than Pluto. It orbits the Sun at an average distance of about 68 astronomical units, taking 558 years to complete one orbit. Eris has one known moon, Dysnomia, and its surface is coated with methane ice that appears to be constantly refrozen as it moves through its orbit. Eris is so far from the Sun that its surface temperature is a mind-boggling -405 degrees Fahrenheit. When it reaches its closest approach to the Sun, some of this methane ice vaporizes, creating a very thin atmosphere that then freezes solid again as it moves farther away. Eris's discovery was one of the triggers for reclassifying Pluto as a dwarf planet, because it showed that there are other objects out there similar in size to Pluto, and if Pluto was a planet, then Eris should be too, and likely many others. This led to the International Astronomical Union's controversial decision in 2006 to create the new category of dwarf planet. Haumea is another fascinating world. Discovered in 2003, Haumea is unique because of its extremely rapid rotation. It spins once on its axis every 3.9 hours, making it one of the fastest rotating large objects in the solar system. This rapid spin has stretched Haumea into an elongated shape, like a cosmic football or perhaps a flattened egg, with dimensions of about 980 by 750 by 500 kilometers. Haumea rotates so quickly that if you stood on its surface, you'd experience significant centrifugal force. It has two known moons, Namaka and Hi2bb, and it even has a ring system, discovered in 2017, making it the first known Kuiper Belt object with rings. Haumea's surface is covered in crystalline water ice, which is unusual because this type of ice should be converted to amorphous ice over cosmic timescales due to radiation. The presence of crystalline ice suggests that Haumea has been recently resurfaced, perhaps by cryovolcanic activity or by fresh ice exposed through collisions. Makemake, pronounced Makemake, and named after the creator god of the Rapa Nui people of Easter Island, is another large dwarf planet. Discovered in 2005, Makemake is about 1,500 kilometers in diameter, making it the third largest known Kuiper Belt object after Pluto and Eris. It orbits at about 45.8 astronomical units, taking 305 years to orbit the Sun. Makemake is reddish in color and has one known moon, provisionally designated S2015, 136,472, 1, or MK2, discovered in 2015. This moon is about 175 kilometers in diameter and orbits about 13,000 miles from Makemake. The reddish color of Makemake's surface likely comes from the presence of tholins, organic compounds formed when ultraviolet radiation and cosmic rays bombard simple molecules like methane. These tholins are the same type of compounds that give Pluto and other Kuiper Belt objects their reddish hues. Quawar, discovered in 2002 and named after the creator god of the Tongva Native American tribe, is another impressive dwarf planet candidate. It's about 844 kilometers in diameter, orbiting at about 44 astronomical units with a period of 287 years. Quawar has one known moon, Waywat, and remarkably, it also has a ring system, discovered in 2023. What's particularly interesting about Quawar's rings is where they're located. They orbit at a distance of about 2,500 kilometers from Quawar's surface, which is much farther out than what we thought was possible for rings to exist around such a small body. The Roche limit, which is the distance within which a celestial body would be torn apart by tidal forces, is thought to be much closer in for small bodies like Quawar. The fact that rings exist at this distance challenges our understanding of ring dynamics and suggests we still have much to learn about how ring systems form and survive. Now, I want to dive deeper into this concept of tholins because it's absolutely fascinating, and it connects to one of the most profound questions in science: the origins of life. Tholins are complex organic molecules that form when ultraviolet light or cosmic rays irradiate simple organic compounds like methane, ethane, and nitrogen. This process, called radiolysis, happen slowly over billions of years on the surfaces of Kuiper Belt objects. The result is a reddish, tar-like substance that coats many of these icy worlds. But these aren't just simple chemicals. They're the building blocks of life, or at least potential precursors to life. When scientists like those working on the New Horizons mission see these reddish hues on Pluto, Charon, Haumea, and other objects, they're seeing evidence that the same chemical processes that might have led to life on Earth were happening all across the solar system. These tholins contain amino acids, nucleic acids, and other complex organic molecules that are essential for life as we know it. So these distant, frozen worlds aren't just dead rocks. They're chemical laboratories that have been running experiments for billions of years, potentially creating the ingredients that could seed life throughout the cosmos. The surfaces of these objects tell stories of dramatic geological activity that we never expected to find so far from the Sun. Take Pluto again. The New Horizons mission revealed that it's geologically active, with glaciers of nitrogen ice that flow across the surface, mountains of water ice that rise up to 3.5 kilometers high, and vast plains where convection cells slowly turn over the surface material. The lack of impact craters in regions like Sputnik Planitia tells us that the surface is being constantly renewed, with fresh ice covering older terrain. This activity shouldn't be possible on such a small world so far from the Sun, where the solar energy is less than 1% of what reaches Earth. The heat must be coming from within. Pluto's interior likely contains radioactive elements like uranium, thorium, and potassium that release heat as they decay. Over billions of years, this heat has built up, possibly melting parts of Pluto's interior and creating a subsurface ocean. This heat might also drive cryovolcanism, where slushy water and ice erupt onto the surface like volcanoes, but instead of lava, they spew water, ammonia, and methane ices. Charon, Pluto's largest moon, shows similar surprising activity. The New Horizons images revealed that Charon has a reddish polar cap, nicknamed Mordor macula, which scientists believe is formed when methane gas escaping from Pluto's atmosphere gets trapped at Charon's cold poles and is converted into tholins by radiation. But some researchers have proposed an even more intriguing possibility, that Charon underwent cryovolcanic eruptions early in its history, releasing methane from its own interior. This process would be similar to silicate volcanism on Earth, but with ice instead of rock. The idea is that Charon's interior melted, creating slushy water mixed with ammonia and methane, which then erupted onto the surface, releasing methane gas that eventually migrated to the poles. This hypothesis, if true, would mean that even mid-sized icy moons can have complex geological histories driven by internal heating. The exploration of these distant worlds reached a milestone with the New Horizons mission, which has been our only spacecraft to visit the Kuiper Belt up close. After its historic flyby of Pluto in 2015, New Horizons continued deeper into the Kuiper Belt, targeting an object called Arrokoth, which was known as Ultima Thule before its official naming. Arrokoth is a contact binary, meaning it's two objects that have gently touched and stuck together, forming a shape like a snowman or a lopsided dumbbell. When New Horizons flew past Arrokoth on New Year's Day 2019, it was the most distant object ever visited by a spacecraft, over 4 billion miles from Earth. The images revealed a world unlike anything we'd seen before. The two lobes, named Ultima and Thule during the encounter, appear to have formed from two separate objects that gently collided at extremely low speeds, perhaps just a few miles per hour. This gentle merger is significant because it suggests that the building blocks of planets formed through a process of slow accretion, where small particles gradually stuck together, rather than through high-speed collisions that would have shattered them. Arrokoth's surface is also remarkable for what it doesn't have: impact craters. The object appears to be remarkably smooth, with only a few small craters visible. This suggests that it's been relatively undisturbed since it formed over 4 billion years ago. Its red color indicates the presence of tholins, and the subtle surface features hint at ancient processes that we don't yet fully understand. The discovery that Arakoth is a contact binary provides direct evidence for how planetesimals, the building blocks of planets, formed through hierarchical accretion. Small particles stuck together to make larger ones, which then stuck together to make even larger ones, eventually forming the dwarf planets and perhaps, in other circumstances, full-sized planets. Binary systems are actually quite common in the Kuiper Belt. In addition to Pluto, which is the quintessential binary system, where both bodies are similar enough in size that they orbit a common center of mass outside either body. About 80 other KBOs have been found to have binary companions. Some of these are near-equal binaries where both objects are similar in size, making it hard to determine which is the primary and which is the moon. Others have much smaller companions. The prevalence of binary systems tells us something important about the environment in which these objects formed. The fact that so many binaries exist suggests that collisions in the early Kuiper Belt were relatively gentle, at low velocities, allowing objects to capture each other gravitationally without shattering. This is different from the violent, high-speed collisions that were common in the inner solar system. The binary systems are like cosmic diaries, recording the conditions of the early outer solar system in their orbital characteristics. The study of these distant objects requires incredibly sophisticated technology and clever techniques. Since we can't visit most of them with spacecraft, New Horizons was a rare and expensive exception. Astronomers rely on Earth-based and space-based telescopes to learn what they can. The challenge is immense. These objects are incredibly faint because they're so far away and reflect so little sunlight. To detect them, astronomers use large telescopes on mountaintops like Mauna Kea in Hawaii, or in space with the Hubble Space Telescope, and now the James Webb Space Telescope. They take long exposure images, sometimes hours long, to collect enough photons to see these distant worlds. They use sophisticated computer algorithms to compare images taken at different times, looking for objects that move against the background stars. This technique, called digital tracking or shifting and stacking, allows them to detect objects that would otherwise be invisible. Once an object is discovered and its orbit determined, astronomers can study its physical properties. They measure its brightness over time to determine its rotation period, how fast it spins. They analyze its color by taking images through different filters, which gives clues about its surface composition. For brighter objects, they can take spectra, breaking the light into its component colors to identify specific molecules like water ice, methane, and complex organics. The James Webb Space Telescope is revolutionizing this field because its infrared capabilities are perfect for studying these cold, distant objects. Infrared light is better at detecting the thermal emission from these icy bodies, and many of the spectral signatures of ices and organic compounds are strongest in the infrared. JWST can tell us not just that water ice exists on these objects, but what form it's in, whether it's crystalline or amorphous, which tells us about the object's thermal history and whether it's been heated since it formed. When we do get the rare opportunity to visit these objects with spacecraft like New Horizons, the instruments on board are marvels of engineering. The Long-Range Reconnaissance Imager, or LORRI, is essentially a digital camera with an 8.2-inch telescope, capable of taking incredibly detailed images from millions of miles away. The RALPH instrument is a combination of cameras and spectrometers that can take color images and spectra in both visible and infrared light, mapping the surface composition and temperature. The ALICE instrument is an ultraviolet spectrometer that studies the composition of any atmospheres these objects might have and looks at how sunlight interacts with their surfaces. The radio science experiment uses the spacecraft's radio signals to measure the mass and density of objects by precisely tracking how their gravity affects the spacecraft's trajectory. By combining all these instruments, scientists can build a comprehensive picture of these distant worlds, their shapes, sizes, compositions, surface features, internal structures, and orbital characteristics. Now, I want to talk about one of the most mysterious and controversial aspects of the Kuiper Belt, the possible existence of Planet 9. In 2016, astronomers Konstantin Batygin and Mike Brown at Caltech proposed that a large, undiscovered planet might be lurking in the distant outer solar system, far beyond the Kuiper Belt. They didn't see this planet directly, nobody has yet, but they inferred its existence from the unusual orbits of some extreme trans-Neptunian objects, or ETNOs. These are objects with very elongated orbits that take them hundreds of astronomical units away from the Sun. What Batygin and Brown noticed was that several of these ETNOs had orbits that were clustered together in space. They all approached their closest point to the Sun, their perihelion, at roughly the same location, and their orbits were tilted in similar ways. The chances of this happening randomly are incredibly small, about 0.007%, or roughly 1 in 14,000. Something must be shepherding these objects, keeping them in this alignment. Their hypothesis suggests that Planet 9 is a massive planet, perhaps 5 to 10 times the mass of Earth, about the size of a super-Earth, or a mini-Neptune. This hypothetical world would orbit the Sun on a highly elliptical path, taking 10,000 to 20,000 years to complete one orbit. At its closest approach, it might be around 200 astronomical units from the Sun, already far beyond the Kuiper Belt. At its most distant point, it could be 600 to 1,200 astronomical units away, approaching the inner edge of the Oort cloud. Its gravity would be strong enough to sculpt the orbits of these extreme trans-Neptunian objects, creating the clustering that we see. The search for Planet 9 has been intense. Astronomers have used powerful telescopes like the Subaru telescope in Hawaii, the Dark Energy Survey in Chile, and data from the Wide Field Infrared Survey Explorer WISE space telescope to scan huge swaths of the sky, looking for this elusive world. So far, despite years of searching, no direct detection has been made. This could mean several things. Maybe Planet 9 doesn't exist at all, and there's another explanation for the orbital clustering. Maybe it's smaller and darker than predicted, making it harder to detect. Maybe it's currently at the far point of its orbit, making it extremely faint and distant. Or maybe it's located in a part of the sky that's difficult to observe, perhaps obscured by the dense star fields of the Milky Way. Not everyone is convinced that Planet 9 exists. Some astronomers argue that the apparent clustering of ETNO orbits might be an observational bias. Because these objects are so faint, we can only detect them when they're near their closest approach to the Sun. And ground-based telescopes can only survey certain parts of the sky, particularly away from the bright Milky Way. This could create the illusion of clustering where none exists. Dr. Samantha Lawler, an astronomer at the University of Regina, has conducted careful surveys trying to find these extreme objects in a uniform way around the entire sky. Her results suggest that when you account for these observational biases, the clustering might disappear. The distribution could be uniform. Other studies using data from the Dark Energy Survey have reached similar conclusions. The debate is ongoing, with Planet 9 proponents arguing that we haven't discovered enough of these extreme objects yet to make a definitive statistical conclusion. Alternative explanations have also been proposed. One idea is that instead of a single large planet, a massive disk of smaller objects in the outer solar system could be collectively exerting enough gravitational influence to sculpt the orbits of ETNOs. This disk would need to be massive, perhaps several Earth masses in total, spread across a wide region of space. Another hypothesis suggests that the clustering could be a temporary effect, created by a close encounter with a passing star or rogue planet in the solar system's distant past, perhaps just a few 100 million years after it formed. Such an encounter could have gravitationally perturbed the outer solar system, creating the orbital patterns we see today. Yet another controversial theory involves modified Newtonian dynamics, or MOND, which proposes that our understanding of gravity breaks down at very low accelerations, like those experienced by objects in the distant outer solar system. According to MOND, the observed orbital patterns could be explained without any missing planet at all, just by the collective gravitational influence of the Milky Way stars on the outer solar system. This scientific debate is a perfect example of how science works at its best. We have observations that don't quite fit our current models, so we propose hypotheses to explain them. Then we make predictions and conduct observations to test those hypotheses. Some evidence supports Planet 9, other evidence contradicts it, and the scientific community debates, refines its models, and searches for more data. The upcoming Vera Rubin Observatory, scheduled to begin its sky survey in 2025, might finally resolve this question. Its powerful telescope and huge camera will be able to survey the entire southern sky every few nights, potentially discovering thousands of new Kuiper Belt objects and extreme trans-Neptunian objects. If Planet 9 exists, Vera Rubin should be able to detect it directly, or at least find enough ETNOs to determine whether the clustering is real or just a statistical fluke. Beyond the Kuiper Belt lies an even more mysterious region, the Oort cloud. While the Kuiper Belt is a relatively flat disk in the plane of the solar system, the Oort cloud is a giant spherical shell that surrounds the entire solar system. It's thought to start somewhere between 2,000 and 5,000 astronomical units from the Sun, extending out to perhaps 100,000 astronomical units, which is about 1.5 light-years, nearly halfway to the nearest star. Unlike the Kuiper Belt, we've never directly observed the Oort cloud. It remains theoretical, inferred from the orbits of long-period comets that plunge into the inner solar system from all directions. These comets have orbits that are so long and so random that they can't be coming from the flattened Kuiper Belt. Instead, they must originate from a spherical reservoir of icy bodies, the Oort cloud. The Oort cloud is believed to contain trillions of comets, remnants from the formation of the solar system that were ejected to these extreme distances by gravitational interactions with the giant planets during the Nice model instability. While the Kuiper Belt is the source of short-period comets that orbit in less than 200 years, the Oort cloud is the source of long-period comets that can take thousands or even millions of years to complete one orbit. Comets like Comet Hale-Bopp and Comet Hyakutake are thought to be Oort cloud objects that were perturbed by the gravity of nearby stars or the Milky Way itself, sending them falling toward the inner solar system. When we see these magnificent comets with their long, brilliant tails, we're seeing ambassadors from the most distant reaches of our solar system, from a region so far away that it's barely held by the Sun's gravity. The distinction between the Kuiper Belt and the Oort cloud is important. The Kuiper Belt is relatively well studied. We've discovered thousands of objects, visited two with spacecraft, and we understand its basic structure and composition. The Oort cloud remains largely theoretical. It's so distant that even our most powerful telescopes can't see individual objects there. The Voyager 1 spacecraft, which has been traveling for over 45 years and is now over 150 astronomical units from the Sun, won't enter the Oort cloud for another 300 years, and it will take 30,000 years to pass through it. The Oort cloud represents the true edge of the Sun's gravitational influence, the boundary between our solar system and interstellar space. Now let's talk about the future of Kuiper Belt exploration, because we're just getting started. The New Horizons mission, while revolutionary, was just a first taste. It flew past Pluto and Arrokoth, giving us detailed views of two objects out of potentially millions. Imagine what we could learn if we could study dozens or hundreds of these objects up close. The challenge, of course, is distance. It took New Horizons 9 years to reach Pluto, traveling at speeds of over 36,000 miles per hour. Getting to other Kuiper Belt objects requires enormous amounts of time and fuel, or some breakthrough in propulsion technology. However, there are exciting possibilities on the horizon. One concept is to send a dedicated Kuiper Belt explorer, perhaps using advanced electric propulsion like ion drives, which can accelerate spacecraft to much higher speeds over time. Another idea is to use solar sails, giant reflective sheets that use the pressure of sunlight to slowly but continuously accelerate. A solar sail mission could potentially reach the Kuiper Belt much faster than conventional rockets. There's also the possibility of using gravity assists, slingshotting around planets to gain speed, though this is tricky for reaching the outer solar system. Another exciting development is the rise of small, low-cost spacecraft. CubeSats and SmallSats are tiny satellites that can be built and launched for a fraction of the cost of traditional flagship missions. While a single large spacecraft like New Horizons costs hundreds of millions or even billions of dollars, a fleet of small spacecraft could potentially be sent to the Kuiper Belt for the same price, each targeting a different object. They wouldn't have the same sophisticated instruments as a flagship mission, but they could provide valuable reconnaissance, helping us prioritize targets for future, more detailed exploration. The James Webb Space Telescope is already revolutionizing our understanding from afar. Its infrared capabilities are perfect for studying these cold, distant objects, and it's already making breakthrough observations. JWST can study the compositions of KBOs in detail, looking for specific molecules and ices. It can measure their thermal properties, telling us about their surface temperatures and how quickly they cool. It can even search for signs of activity, like outgassing or cryovolcanism, that would be invisible to other telescopes. As JWST continues its observations, we'll build up an unprecedented database of Kuiper Belt object properties. Ground-based telescopes are also becoming more powerful. The Vera Rubin Observatory, which I mentioned earlier, will be transformative. Its 8.4-meter mirror and 3,200 megapixel camera, the largest digital camera ever built, will allow it to image the entire southern sky every 3 nights. It will discover thousands, perhaps tens of thousands, of new Kuiper Belt objects, particularly the rare and distant ones that can help us solve the Planet 9 mystery. The extremely large telescope, currently under construction in Chile, will have a 39-meter mirror, making it the largest optical telescope in the world. It will be able to directly image and study Kuiper Belt objects in unprecedented detail, perhaps even resolving surface features on the largest ones. But let's dream even bigger. What about sending humans to the Kuiper Belt? This is firmly in the realm of science fiction for now, but it's fun to think about. The challenges are enormous. It would take decades to get there, requiring life support systems that can function for generations, or some form of hibernation or suspended animation. We'd need radiation shielding to protect against cosmic rays and solar flares. We'd need propulsion systems far beyond what we have today. But if we could do it, what would we find? We could establish research stations on dwarf planets like Pluto or Eris, drilling through their icy surfaces to explore subsurface oceans. We could mine these objects for resources, water ice for life support and fuel, methane and ammonia for chemical processing, perhaps even precious metals from their rocky cores. The Kuiper Belt could become the frontier for human expansion into the outer solar system, a stepping stone to the stars. Now let's get philosophical for a moment. Why does any of this matter? Why should we care about these distant, frozen worlds that most people will never see? I think it matters for several profound reasons. First, these objects are our origins. They are the leftovers from the formation of the solar system, the building blocks that never became planets. By studying them, we're studying where we came from, the conditions that existed when Earth was just forming. They can tell us about the delivery of water and organic materials to the inner solar system, materials that might have been crucial for the origin of life on Earth. Many scientists believe that Earth's water didn't all come from here originally, that much of it was delivered by comets and asteroids from the outer solar system. The Kuiper Belt objects are the source of those comets, so by understanding them, we understand our own history. Second, they challenge our assumptions about what's possible. For decades, we assumed that small, distant worlds would be geologically dead, frozen solid and unchanging. Pluto proved us wrong. We assumed that rings could only exist close to planets within their Roche limit. Kuiper proved us wrong. We assumed that binary systems would be rare. The Kuiper Belt proved us wrong. These discoveries teach us humility and show us that nature is far more creative and interesting than our theories often predict. Every time we look closely at these objects, we find something unexpected, something that forces us to rewrite our textbooks. Third, they represent the future of exploration. The Kuiper Belt is the next frontier, the next step in our journey as a spacefaring species. Just as the exploration of the Moon taught us how to live in space, and Mars will teach us how to build sustainable colonies, the Kuiper Belt will teach us how to survive in the deep outer solar system. It will push our technology to new limits, forcing us to develop better propulsion, better life support, better radiation shielding, better autonomous systems. The challenges we solve to explore the Kuiper Belt will be the same challenges we need to solve to one day explore other star systems. Fourth, they connect us to the broader universe. The Kuiper Belt isn't unique to our solar system. As we discover planets around other stars, we now understand that these systems likely have their own Kuiper Belts, their own reservoirs of icy remnants. These exo-Kuiper Belts, as we call them, can tell us about the formation and evolution of other planetary systems. We can see them indirectly when we observe dusty disks around other stars, the debris from collisions between Kuiper Belt-like objects. We can infer their presence when we see comet-like activity around other stars. By understanding our own Kuiper Belt, we gain the tools to understand planetary systems throughout the galaxy, placing our own solar system in context. Finally, there's something deeply human about this quest for knowledge. Since the dawn of consciousness, we've looked up at the night sky and wondered what's out there. The Kuiper Belt represents one of the last great unknowns in our cosmic backyard. It's a reminder that there's still so much to discover, still so many mysteries to solve. It inspires wonder and curiosity, the same feelings that drove our ancestors to explore new continents and cross vast oceans. In exploring the Kuiper Belt, we're continuing that great human tradition of pushing boundaries, of seeking to understand our place in the universe. Let's dive deeper into some of these objects and their unique characteristics, because each one tells a different part of the story. Take Sedna, for example, discovered in 2003. Sedna is one of the most distant objects we know of, with an incredibly elliptical orbit that takes it from 76 astronomical units at its closest approach all the way out to 975 astronomical units at its most distant, a journey that takes over 11,000 years to complete. Sedna is so far out that it's not really influenced by Neptune's gravity anymore. Its orbit is a mystery. How did it get out there? Some scientists think it might have been pulled by a passing star early in the solar system's history. Others suggest it could be evidence for Planet 9. Still others think it might be an inner Oort cloud object rather than a true Kuiper Belt object. Sedna's existence tells us that there are still massive surprises lurking in the outer solar system, populations of objects we haven't even begun to understand. Then there's Gong Gong, another large Kuiper Belt object discovered in 2007. Gong Gong is about 1,230 kilometers in diameter and has a moon named Xiangliu. What's interesting about Gong Gong is its extremely reddish surface, one of the reddest objects in the solar system. This suggests an unusually high concentration of tholins, perhaps indicating that it's rich in organic materials. Gong Gong also has a relatively high orbital inclination, meaning its orbit is tilted significantly compared to the plane of the solar system. This suggests it was gravitationally scattered into its current orbit, perhaps by Neptune or another migrating planet. Orcus is another fascinating object, discovered in 2004. Orcus is sometimes called the anti-Pluto because it's in a similar orbit to Pluto but on the opposite side of the solar system. It has a 3 resonance with Neptune just like Pluto, but its orbit is oriented differently. Orcus has a moon, Vanth, that's about half its size, making it another interesting binary system. The surfaces of both Orcus and Vanth appear to be covered in water ice and possibly methane ice, and their similar colors suggest they may have formed from the same material, or that Vanth formed from debris after a giant impact on Orcus. The diversity among these objects is astounding. Some, like the cold classical objects, appear to have remained unchanged since the solar system formed. Others, like the hot classical and scattered objects, show evidence of being moved and mixed. Some have moons, some have rings, some are red, some are gray, some are active, some are dead. Each one is a unique world with its own story to tell, and we haven't even discovered most of them yet. Scientists estimate that there are hundreds of thousands of objects larger than 100 kilometers that we haven't found, and millions of smaller ones. The detection of rings around small bodies like Kuiper and Haumea has been particularly surprising because it challenges our understanding of ring dynamics. The Roche limit is the distance within which a celestial body would be torn apart by tidal forces from the planet it orbits. For small bodies like Kuiper, this limit should be quite close to the surface. Yet Kuiper's rings orbit much farther out, at a distance where they should have been pulled apart or pulled into the dwarf planet. This suggests that either our understanding of the Roche limit is incomplete for small bodies, or that there's some mechanism holding these rings together that we don't yet understand. Perhaps the rings are made of very small particles that are held together by cohesive forces, or maybe there's a small moonlet in the rings that provides some stability. Whatever the explanation, it's clear that the Kuiper Belt is still full of surprises. The presence of these rings also tells us about the environment in which they formed. Rings around giant planets like Saturn are thought to form either from the debris of shattered moons or from material that was left over from the planet's formation and never coalesced into a moon. For small bodies like Kuiper, the rings could have formed from the debris of a collision. Perhaps a small moon got too close and was torn apart, or two objects collided and created a debris field. Alternatively, they could be made of material that's slowly escaping from the dwarf planet itself, perhaps through cryovolcanic activity or through the sublimation of ices on the surface, creating a tenuous atmosphere that then condenses into rings. Each possibility tells us something different about the object's history and internal processes. Now, let's talk about some of the other scientific mysteries these objects can help solve. One big question is about the isotopic composition of the solar system. The ratio of different isotopes, different versions of elements with different numbers of neutrons, can tell us about where and when material formed. For example, the ratio of deuterium to hydrogen in water can tell us whether that water formed in the hot inner solar system or in the cold outer solar system. By studying the isotopic composition of Kuiper Belt objects, either through direct sampling of comets or through remote spectroscopy, scientists can map out how material moved around the early solar system. Some meteorites that fall to Earth contain grains that formed in the outer solar system, based on their isotopic signatures. These grains provide direct samples of the same material that makes up Kuiper Belt objects, giving us ground truth for our remote observations. Another mystery is the missing mass problem. When astronomers add up all the mass in the Kuiper Belt and scattered disk, it only amounts to about a tenth of Earth's mass, or roughly the mass of Mars. But models of planet formation suggest that to grow objects as large as Pluto and Eris, there should have been much more mass out there originally, perhaps several Earth masses. So where did all that mass go? The NICE model provides an answer. Most of it was ejected by Jupiter during the giant planet instability. But this raises another question. Do we have enough evidence to confirm this mass loss? Some scientists think there might still be a large population of objects that we haven't detected because they're too small or too dark. Others suggest that the mass might be hidden in the form of dust, created by collisions over billions of years, that's slowly being blown out of the solar system by solar radiation pressure. Another possibility is that the original mass estimates are wrong, and the Kuiper Belt never contained as much material as we thought. The collisional history of the Kuiper Belt is another active area of research. By counting impact craters on objects like Pluto and Eris, scientists can estimate how often collisions occur. The surprising lack of small craters on Pluto's Sputnik Planitia suggests that there are fewer small objects in the Kuiper Belt than expected, or that some process is erasing the craters. This could mean that the size distribution of Kuiper Belt objects is different than predicted by models of collisional evolution. Perhaps the smallest objects are being destroyed by collisions faster than we thought, or being swept up by larger objects. Alternatively, the geological activity on Pluto might be erasing craters through resurfacing. Understanding this collisional history is important because it tells us about the current population of objects and helps us predict how the Kuiper Belt will evolve in the future. The future evolution of the Kuiper Belt is itself an interesting question. Over billions of years, the Kuiper Belt is slowly eroding. Objects collide and break apart, creating smaller fragments and dust. This dust is then pushed out of the solar system by solar radiation pressure and the solar wind. Some objects are perturbed by Neptune's gravity and sent into the scattered disk or ejected entirely. Over timescales of billions of years, the Kuiper Belt will continue to lose mass and objects. Eventually, perhaps in tens of billions of years, it might be depleted entirely. Of course, by that time, the Sun itself will have become a red giant and engulfed the inner planets, so the Kuiper Belt's fate will be the least of our concerns. But it's fascinating to think about the long-term evolution of our solar system. The Kuiper Belt also has practical implications for space exploration and planetary defense. As we send more spacecraft to the outer solar system, we need to understand the hazard posed by small Kuiper Belt objects. While collisions are extremely rare due to the vast distances involved, a small object could still damage or destroy a spacecraft traveling at high speeds. Understanding the size distribution and spatial density of objects helps mission planners design appropriate shielding and avoidance strategies. This is similar to how we track near-Earth asteroids to protect spacecraft and potentially our planet. Furthermore, the Kuiper Belt could be a resource for future space missions. Water ice can be split into hydrogen and oxygen for rocket fuel. Methane and ammonia could be used for chemical processing or as fuel for nuclear thermal rockets. The low gravity of these objects makes them relatively easy to land on and take off from, compared to planets. Future robotic missions might visit these objects not just for science, but to mine resources that could support a deep space economy. A spacecraft traveling to the stars might stop at a Kuiper Belt object to refuel, what some call a space gas station. While this sounds like science fiction, the physics and economics are being studied seriously by space agencies and private companies. Now, let's consider the astrobiological potential of Kuiper Belt objects. While we think of life as needing liquid water and energy from a star, there are alternative possibilities. Subsurface oceans on objects like Pluto, kept liquid by radioactive heating, could potentially harbor life. These would be truly alien environments, perhaps based on different biochemistries than life on Earth. The genetic building blocks might not be DNA, but some other complex molecule. The energy sources might not be sunlight, but chemical reactions between rocks and water. While we have no evidence that life exists on any Kuiper Belt object, the possibility can't be ruled out. The fact that we keep finding liquid water in unexpected places, on Pluto, on the moons of Jupiter and Saturn, perhaps even on some Kuiper Belt objects, suggests that habitable environments might be much more common in the universe than we once thought. The search for life, or at least the precursors to life, is one reason scientists are so interested in the organic chemistry happening on these objects. The tholins we discussed earlier are complex organic molecules that could be the starting point for prebiotic chemistry. If these molecules could be delivered to subsurface oceans through cryovolcanic activity or impacts, and if there's an energy source, you have the basic ingredients for life. While the timescales are enormous and the conditions are extreme, life on Earth also started under conditions that seemed impossible until we understood the processes involved. The study of Kuiper Belt objects helps us understand the distribution of organic materials throughout the solar system, which is crucial for understanding both the origin of life on Earth and the possibility of life elsewhere. The cultural and philosophical impact of Kuiper Belt exploration shouldn't be underestimated either. The New Horizons flyby of Pluto captured the world's imagination in a way that few space missions have. Pluto went from being a blurry smudge in our telescopes to being a real world with real geology, real complexity, real beauty. People connected with Pluto in a way they hadn't before. The images of its heart-shaped plain, its ice mountains, its blue atmospheric haze, they made Pluto feel like a place, a destination, not just a point of light. This matters because public support for space exploration depends on people feeling connected to the cosmos. When we see these distant worlds up close, when we give them names and personalities, they become part of our shared human experience. The Kuiper Belt becomes not just a scientific concept, but a real frontier, a place of wonder and mystery. The naming of Kuiper Belt objects also reflects our growing understanding and appreciation of world cultures. Many of these objects are named after creation deities from various cultures around the world. Quawar from the Tongva, Makemake from the Rapa Nui, Gonggong from Chinese mythology, Sedna from Inuit mythology. This is a beautiful recognition that the exploration of space is a human endeavor that belongs to all of humanity, not just one culture or nation. It's a way of honoring the rich tapestry of human storytelling and our shared fascination with creation and the cosmos. As we look to the future, there are several key missions and projects that will transform our understanding of the Kuiper Belt in the coming decades. The Vera Rubin Observatory, as I've mentioned, will be revolutionary. Its Legacy Survey of Space and Time, or LSST, will discover so many new objects that we'll have to completely rewrite our classification schemes and dynamical models. It will find objects that are currently too faint to detect, including more extreme trans-Neptunian objects that can help solve the Planet 9 mystery. It will also find more interstellar objects like Oumuamua, which passed through our solar system in 2017. Understanding these visitors from other star systems helps us place our Kuiper Belt in a broader context. The European Space Agency's Ariel mission, launching later this decade, will study exoplanet atmospheres, but its instruments could also be used to study Kuiper Belt objects. The Nancy Grace Roman Space Telescope, NASA's next flagship astrophysics mission, will have a wide field of view and sensitive detectors that make it excellent for finding faint, distant objects. While its primary mission is to study dark energy and exoplanets, it will certainly contribute to Kuiper Belt science. On the ground, the extremely large telescope and the 30-meter telescope will provide unprecedented views of Kuiper Belt objects. These telescopes will be able to resolve surface features on the largest dwarf planets, perhaps even seeing large craters or surface color variations. They'll be able to study the atmospheres of these objects when they approach the sun and begin to develop temporary atmospheres. They'll be able to search for more moons and rings around these objects. In terms of dedicated missions, there are several concepts under study. One is a New Horizons 2 mission, which would send a similar spacecraft to explore other Kuiper Belt objects. The challenge is finding targets that are within reach of the spacecraft's trajectory. Unlike New Horizons, which had the benefit of a Jupiter gravity assist to boost its speed, a follow-up mission might need to rely on next-generation launch vehicles like NASA's Space Launch System or SpaceX's Starship, which could send a spacecraft directly to the outer solar system much faster. Another concept is to send a mission to orbit a dwarf planet, perhaps Pluto or Ceres. An orbiter could stay for years, mapping the entire surface in detail, studying changes over time, and using radio science to probe the internal structure. This would be incredibly scientifically valuable but technically challenging, requiring enormous amounts of fuel to slow down and enter orbit around such a distant object. There's also the intriguing possibility of a sample return mission. Imagine bringing a piece of a Kuiper Belt object back to Earth. This would be the ultimate scientific prize, allowing us to study these primordial materials with every instrument in our laboratories. We'd be able to date them precisely, determine their exact composition down to the isotopic level, and search for trapped gases that could tell us about the conditions of the early solar nebula. A sample return from a comet has already been done. NASA's Stardust mission brought back particles from Comet Wild 2. But a sample from a Kuiper Belt object would be even more primitive and scientifically valuable. The technical challenges are immense, requiring a spacecraft to land on a low-gravity object, collect a sample, and return to Earth, a journey that could take decades. Let's also consider the potential for international cooperation in Kuiper Belt exploration. Space exploration has always been both competitive and collaborative. While different nations have their own programs, they often collaborate on missions, sharing instruments, expertise, and costs. The International Solar System Exploration Program, a concept being discussed among space agencies, could involve multiple nations working together on a comprehensive Kuiper Belt exploration campaign. One nation might provide the main spacecraft, another the lander, another the instruments, another the deep space communications network. This kind of cooperation not only makes these expensive missions more feasible, but it also reflects the fact that space exploration is a shared human endeavor. The educational and inspirational value of Kuiper Belt exploration can't be overstated. Every time we visit a new world, we create new opportunities to inspire the next generation of scientists, engineers, and explorers. The New Horizons mission inspired countless young people to study STEM fields. Imagine the inspiration that would come from a mission that lands on a Kuiper Belt object, or from the discovery of life in a subsurface ocean. These aren't just scientific endeavors, they're investments in our future, in human potential. Now, let's discuss some of the specific scientific questions that future missions might answer. One major question is about the internal differentiation of these objects. Do they have distinct cores, mantles, and crusts like Earth, or are they more homogeneous? Radio science from a flyby or orbiter could measure the mass distribution and tell us if these objects are differentiated. This would tell us about their thermal histories and whether they were ever warm enough to melt and separate into layers. Another question is about their exact composition. While we know they're made of ices, we don't know the exact ratios of water, methane, ammonia, and other compounds, and how these vary from object to object. This would tell us about conditions in different parts of the early solar nebula. A third question is about the presence of atmospheres. Some objects develop temporary atmospheres when they approach the sun, but how thick are they, what are they made of, and how quickly do they freeze out? A fourth question is about magnetic fields. Do any of these objects have residual magnetic fields from ancient dynamos in their cores? This would tell us about their internal evolution and whether they ever had liquid interiors. A fifth question is about the presence of subsurface oceans. We suspect Pluto might have one, but what about other large objects like Eris or Haumea? Detecting these oceans would revolutionize our understanding of where liquid water exists in the solar system. The study of Kuiper Belt objects also helps us understand the impact history of the solar system. By counting craters of different sizes on their surfaces, we can estimate how many impactors of different sizes have hit them over time. This gives us a crater chronology for the outer solar system, which we can compare to the inner solar system. This helps us understand how the populations of asteroids and comets have changed over time, and how the giant planets have moved around, scattering these objects. It also helps us estimate the current hazard level for spacecraft and future human missions. Let's also consider the role of computer simulations in Kuiper Belt science. Because we can't observe these objects directly in most cases, Scientists rely heavily on computer models to understand their formation and evolution. These models use the laws of physics, gravity, orbital mechanics, thermodynamics, to simulate billions of years of solar system history. They start with a disk of material around the young sun and watch how it evolves as planets form and migrate. The best models can reproduce many of the features we see today: the resonant objects, the scattered disk, the hot and cold classical populations, even the binary systems. But these models have many free parameters, and different researchers get different results depending on their assumptions. This is where observations come in. Each new discovery helps constrain the models, ruling out some possibilities and supporting others. It's an iterative process of theory and observation, each informing the other. The NICE model, which I've mentioned several times, is a perfect example of this. When it was first proposed in 2005, it was controversial, but over the years it has successfully explained many different aspects of the outer solar system: the orbits of the giant planets, the Trojan asteroids, the irregular satellites of the outer planets, the structure of the Kuiper Belt. Each successful prediction increases confidence in the model. However, there are still issues to work out. For example, the exact timing of the instability is uncertain. Was it early, shortly after planet formation, or later, around 500–700 million years after formation? The model also doesn't perfectly reproduce all the details of the Kuiper Belt structure, suggesting that our understanding is still incomplete. Some researchers are exploring variations of the NICE model, or entirely different scenarios, to see if they can do better. One exciting development is the use of machine learning and AI in analyzing Kuiper Belt data. With millions of images to analyze from telescopes like Vera Rubin, humans can't possibly look at all of them. AI algorithms can be trained to automatically detect moving objects, classify them based on their brightness and color, and even predict their orbits. This is accelerating the pace of discovery dramatically. AI can also help analyze spectra, identifying molecular signatures in ways that would take humans much longer. As these tools become more sophisticated, they'll help us find patterns and relationships in the data that we might otherwise miss. The international nature of Kuiper Belt research is also worth highlighting. While the largest telescopes and missions have historically been led by the United States and Europe, countries around the world are contributing. Japan has been a major player in asteroid exploration with the Hayabusa missions, and could contribute to Kuiper Belt missions. China is rapidly developing its space program and has ambitious plans for outer solar system exploration. Russia has a long history of planetary exploration. Canada, Australia, and Chile host some of the world's most important observatories. South American and African nations are increasingly participating in astronomical research. This global collaboration enriches the science by bringing different perspectives and expertise. Now, I want to address some common misconceptions about the Kuiper Belt. First, many people confuse it with the Oort cloud. As we've discussed, they're very different. The Kuiper Belt is a relatively nearby, flattened disk, while the Oort cloud is a distant spherical shell. Second, some people think the Kuiper Belt is dangerous, full of debris that spacecraft must constantly avoid. In reality, the objects are so spread out that collisions are extremely rare. New Horizons didn't have to dodge anything on its way to Pluto. The risk was negligible. Third, some people think we know everything there is to know about the Kuiper Belt after the New Horizons mission. In reality, New Horizons visited 2 objects out of millions. We have so much more to learn. Fourth, some people think that because Pluto was reclassified as a dwarf planet, it's somehow less important or interesting. In fact, the opposite is true. The discovery that Pluto is part of this diverse population of fascinating worlds makes it even more scientifically valuable. It's not a lonely oddball at the edge of the solar system. It's the king of a whole class of objects. Let's also talk about the role of amateur astronomers in Kuiper Belt research. While discovering new Kuiper Belt objects generally requires large professional telescopes, Amateurs can contribute in important ways. They can help monitor the brightness of known objects, looking for variations that might indicate rotation or activity. They can help refine orbital measurements by making precise astrometric observations. They can participate in citizen science projects, helping analyze data from professional surveys. And they can help spread awareness and excitement about these discoveries, acting as ambassadors for space science in their communities. Some of the most important discoveries in astronomy have been made by amateurs, and the Kuiper Belt is a frontier where anyone with dedication and the right equipment can make a real contribution. The educational potential is also enormous. Kuiper Belt objects are perfect for teaching about orbital mechanics, planetary formation, spectroscopy, and the scientific method. Students can track the positions of these objects over time, calculating their orbits. They can study their spectra, learning about how different molecules absorb and reflect light. They can debate the Planet 9 hypothesis, learning how to evaluate evidence and arguments. They can design their own missions, thinking about the engineering challenges involved. By connecting abstract scientific concepts to real, tangible worlds, Kuiper Belt studies can inspire the next generation in ways that textbook examples can't. Now, let's explore some of the more exotic possibilities that have been proposed for the Kuiper Belt. One idea is that some of these objects might harbor exotic forms of ice that we don't see on Earth. At the extremely low temperatures out there, ices can form unusual crystalline structures. There might be clathrates, ice that traps gas molecules in its crystal structure, preserving ancient atmospheres from the early solar system. There might be exotic high-pressure ice phases in the interiors of the largest objects, where the pressure from overlying material is sufficient to transform ice into different forms. There might even be liquid water that remains liquid at temperatures far below the normal freezing point, kept in a supercooled state by high pressure and dissolved salts and ammonia. These exotic states of matter could have unusual properties and could tell us about conditions in the early solar nebula that we've never been able to replicate in laboratories. Another exotic possibility is that some Kuiper Belt objects might contain preserved interstellar material. The solar system formed from a molecular cloud that contained material from previous generations of stars. Some of this material might have survived in its original form in the cold, unprocessed Kuiper Belt objects. Finding prosolar grains, tiny particles that formed in other stars before our solar system existed, would give us direct samples of material from across the galaxy. We've found these in meteorites, but the Kuiper Belt might contain a different, more pristine population of prosolar material. Studying this material would tell us about the history of our galaxy and the processes that create and distribute elements across space. There's also the intriguing possibility that some Kuiper Belt objects might be captured interstellar objects themselves. We know that interstellar objects pass through our solar system. Oumuamua and Comet Borisov are recent examples. It's possible that some of these objects could be captured by Neptune's gravity or by resonant interactions and become permanent members of the Kuiper Belt. If we could identify such captured objects, they would give us direct samples of material from other planetary systems, allowing us to compare our solar system's formation and chemistry to that of other stars. This would be revolutionary for understanding whether our solar system is typical or unusual. The connection between the Kuiper Belt and other planetary systems is a rapidly growing field. As we discover more exoplanets and debris disks around other stars, we're learning that many of them have structures that look suspiciously like our Kuiper Belt. The star Fomalhaut, for example, has a prominent debris disk that looks remarkably like a massive Kuiper Belt. Beta Pictoris has a warped disk that might indicate the presence of a migrating planet, just like the NICE model predicts for our solar system. AU Microscopiae has a disk with clumpy structures that might be caused by resonant interactions with planets. By studying these systems and comparing them to ours, we're developing a general theory of planetary system formation and evolution. We're learning that planet migration, resonant capture, and collisional evolution are universal processes that shape solar systems throughout the galaxy. The study of the Kuiper Belt also has implications for understanding dark matter and fundamental physics. Some researchers have proposed that anomalies in the orbits of extreme trans-Neptunian objects could be explained not by Planet 9, but by modifications to our theory of gravity. The modified Newtonian dynamics theory, or MOND, suggests that gravity behaves differently at very low accelerations, which could explain galaxy rotation curves without needing dark matter. If MOND is correct, it might also explain the orbital patterns of Kuiper Belt objects without a new planet. This is highly controversial, and most physicists remain skeptical of MOND. But the fact that Kuiper Belt observations can test fundamental physics shows how important this region is. It's not just a cosmic junkyard, it's a laboratory for testing the laws of nature in extreme conditions. The ethical considerations of Kuiper Belt exploration are also worth discussing. As we consider mining these objects or establishing bases on them, we need to think about preservation. These are scientifically priceless objects, time capsules from the birth of the solar system. If we start mining them or building on them, we could destroy valuable scientific information. There's a debate in the planetary science community about how to balance exploration and exploitation. Some argue that we should designate certain objects as scientific preserves, off-limits to commercial activities. Others argue that the resources are too valuable and that we can learn from the objects we mine. This is part of a broader conversation about space ethics that will become increasingly important as humanity expands into the solar system. The legal framework for Kuiper Belt activities is also unclear. The Outer Space Treaty, signed in 1967, prohibits nations from claiming sovereignty over celestial bodies, but it doesn't clearly address commercial activities or resource extraction. As private companies develop plans to mine asteroids and potentially Kuiper Belt objects, we need to develop new international agreements that balance scientific preservation, commercial interests, and the idea that space should be the common heritage of all humanity. This is an ongoing discussion at the United Nations and among space law experts. Now, let's talk about the technology we'll need to explore the Kuiper Belt more effectively. Current chemical rockets are just barely adequate for reaching the outer solar system, and they take many years. To really open up the Kuiper Belt, we need advanced propulsion. Nuclear thermal propulsion, which was studied in the 1960s and is now being revived, could reduce travel times dramatically. A nuclear thermal rocket heats hydrogen using a nuclear reactor and expels it at high velocity, providing much more thrust than chemical rockets. Another option is nuclear electric propulsion, which uses a nuclear reactor to generate electricity that powers ion thrusters. This provides low thrust but can run continuously for years, slowly building up enormous velocities. Fusion propulsion is a more futuristic option that could provide both high thrust and high efficiency, potentially reaching the Kuiper Belt in just a few years. Solar sails are another promising technology. While sunlight is weak at the Kuiper Belt, a solar sail could be accelerated closer to the sun and then coast out to the outer solar system. Alternatively, a combination of solar sail and electric propulsion could provide flexible, efficient travel. A related concept is the electric sail, which uses the solar wind instead of sunlight to generate thrust. These technologies are being tested now and could be ready for deep space missions in the coming decades. For landing on and exploring these objects, we'll need advanced robotics and AI. The low gravity and extreme cold present unique challenges. A lander might need to anchor itself to the surface with harpoons or drills to avoid drifting away. It might need nuclear heaters to keep its electronics warm in the extreme cold. It will need autonomous systems to make decisions without real-time control from Earth, since the light travel time can be many hours. The rover that explores the surface will need to navigate rugged, icy terrain in low gravity, perhaps using hopping mechanisms rather than wheels. The communication challenges are also significant. At the distance of the Kuiper Belt, radio signals take hours to travel one way. A spacecraft at Pluto is about 4.5 light hours from Earth, meaning a round-trip communication takes 9 hours. This means spacecraft must be highly autonomous. It also means we need large radio telescopes on Earth and powerful transmitters on the spacecraft to communicate. The Deep Space Network is being upgraded with new antennas and technologies to support more outer solar system missions. The science instruments for future missions will also be more advanced. Next-generation spectrometers will be able to identify specific organic molecules with much greater precision. Imaging systems will have higher resolution and better low-light capability. Mass spectrometers will be able to sample thin atmospheres directly. Ground-penetrating radar could probe beneath the surface to look for subsurface oceans or layering. Seismometers could detect quakes that reveal internal structure. Magnetometers could measure magnetic fields. The challenge is making these instruments small, lightweight, and power-efficient enough for long-duration deep space missions. The search for biosignatures is another frontier. Future missions might carry instruments specifically designed to detect signs of life. These could look for specific organic molecules that are produced by biological processes, or isotopic ratios that differ from what we'd expect from non-biological processes. They might look for patterns in the environment that suggest metabolic activity, like chemical gradients or unusual concentrations of certain compounds. While the chances of finding life on a Kuiper Belt object are slim, the potential payoff is so enormous that it's worth looking. The study of Kuiper Belt objects also informs our understanding of planetary protection. When we send missions to potentially habitable worlds, we need to be careful not to contaminate them with Earth life. The same applies to Kuiper Belt objects if they have subsurface oceans. NASA and other space agencies have planetary protection protocols that require sterilizing spacecraft that might contact potentially habitable environments. As we explore more of these objects, we'll need to develop specific protocols for the outer solar system, balancing the need for clean exploration with the practicalities of mission design. Now let's think about the long-term future beyond just exploration. Could humans ever live in the Kuiper Belt? This seems like pure science fiction, but let's consider it. The first challenge is energy. Solar power is weak at these distances. Pluto receives less than 1% of the sunlight that Earth does. So you'd need enormous solar arrays, or more likely, nuclear power. A small nuclear reactor could provide reliable power for a base. The second challenge is resources. As I mentioned, water ice is abundant and can be split into oxygen for breathing and hydrogen for fuel. Methane and ammonia could provide additional chemical resources. The third challenge is radiation. Without a protective magnetic field and atmosphere, Kuiper Belt objects are exposed to cosmic rays. You'd need to live underground or under thick ice shielding. The fourth challenge is isolation. Communication with Earth would be slow, and resupply missions would be rare and expensive. A Kuiper Belt colony would need to be almost entirely self-sufficient. This would require advanced closed-loop life support systems, 3D printing for manufacturing spare parts, and sophisticated agriculture or food production systems. If these challenges could be overcome, there are potential benefits. The low gravity could be beneficial for certain industrial processes. The abundance of volatiles could support a space-based economy. The distance from the sun means less solar radiation and more stable thermal environments. And there's the pure scientific value of having humans on site to conduct research, make repairs, and respond to discoveries in real time. A base on Pluto, for example, could study its atmosphere, geology, and potential subsurface ocean in ways that robots simply can't match. Of course, we're talking about a future that's probably centuries away, if it ever happens. but it's worth thinking about because it stretches our imagination and forces us to solve problems that will benefit us here on Earth. Developing closed-loop life support for a Pluto base could help us develop better life support for submarines or space stations. Developing radiation shielding could help protect people from radiation here on Earth. The technological spin-offs from space exploration have always benefited society, and extreme environment exploration pushes those benefits even further. The cultural and psychological aspects of such a mission would also be profound. The first humans to travel to the Kuiper Belt would be true pioneers, going farther from Earth than any human has ever gone. They would experience isolation and communication delays that no astronaut has faced. They'd see the sun as just a bright star, providing minimal warmth and light. They'd look up at a sky where the constellations are the same as on Earth, but the planets are mere points of light. The psychological preparation for such a journey would be as important as the technical preparation. They'd be explorers in the truest sense, like the ancient mariners who crossed oceans not knowing what they'd find. Now let's bring it back to the present and why you should care about all of this today. Understanding the Kuiper Belt helps us understand our place in the cosmos. It reminds us that our solar system is a dynamic, evolving system, not a static one. It shows us that the processes that shaped our world, collisions, migrations, resonances, are universal. It demonstrates that the distinction between planets and other objects is not always clear-cut, forcing us to think more carefully about how we categorize and understand celestial bodies. It provides a context for understanding exoplanetary systems, most of which probably have their own Kuiper belts. And it gives us a glimpse into the distant future of our solar system, when the sun becomes a red giant and the inner planets are destroyed. The Kuiper Belt objects will survive, perhaps becoming the last remnants of our solar system. The Kuiper Belt is also a reminder of how much we have left to discover. In an age where it sometimes feels like we've explored everything, the Kuiper Belt shows us that there are still vast unknown territories in our own cosmic backyard. Each new object discovered, each new mission planned, each new theory proposed, expands our understanding and reminds us that science is never finished. There's always another mystery to solve, another question to answer, another frontier to explore. Before I wrap this up, I want to revisit that call to action I made at the beginning. If you're watching this and you haven't already, please take a moment to like this video if you found it interesting. The YouTube algorithm really does favor engagement, and liking helps more people discover this content. If you're new here, hit that subscribe button and ring the notification bell so you don't miss future videos where we dive deep into other cosmic mysteries. And please leave a comment telling me where you're watching from and what time it is. I genuinely love seeing responses from people in different countries and time zones. We have community members from every continent, from tiny island nations to massive continents, watching at all hours of the day and night. It creates this incredible global conversation about our shared passion for space. So drop a comment. Are you watching from a bustling city, a quiet rural town, a research station in Antarctica? I want to hear from you. Now, as we reach the end of our journey today, I want to leave you with a sense of wonder and possibility. We've traveled from the inner edge of the Kuiper Belt at Neptune's orbit, out past Pluto and Arrokoth, through the scattered disk, toward the hypothetical Oort cloud. We've met dwarf planets with exotic properties, binary systems dancing in the dark, objects with surprising geological activity, and mysteries that have scientists debating fundamental physics. We've seen how these ancient icy bodies preserve the story of our solar system's birth, how they serve as waypoints for future exploration, and how they challenge us to think bigger about our place in the universe. The Kuiper Belt is more than just a collection of frozen rocks. It's a frontier in every sense of the word, a scientific frontier where every discovery changes our understanding, a technological frontier that pushes our engineering capabilities, a philosophical frontier that makes us question our assumptions, and perhaps someday, a human frontier where we'll venture to explore in person. It's a reminder that exploration isn't just about going where others have gone before. It's about venturing into the unknown, armed with curiosity and the tools of science, ready to be surprised. So the next time you look up at the night sky, remember that beyond the planets you can see with your naked eye, beyond the asteroids and comets that occasionally visit our neighborhood, there's a vast and mysterious realm of icy worlds, each one unique, each one holding secrets billions of years old. They're out there right now, silently orbiting, waiting for us to visit again, to reveal more of their mysteries. And every time we do, we learn not just about them, but about ourselves, about our origins, and about our future. Thank you so much for joining me on this incredible journey today. I hope you've enjoyed exploring the Kuiper Belt's hidden worlds as much as I've enjoyed sharing them with you. If you're watching this in the morning, have a fantastic day. If it's afternoon, I hope the rest of your day is wonderful. And if it's night where you are, I wish you good night, sweet dreams, and maybe dream of distant icy worlds orbiting silently in the dark. Wherever you are, whatever time it is, thank you for being part of this amazing community of space enthusiasts. Keep looking up, keep wondering, keep questioning, and never stop exploring. Until next time, this is your host signing off from wherever I am, sending you all my best wishes and cosmic hugs. Goodbye for now and good night.